CLion, a cross-platform IDE for C and C++. Download now.
So hello and welcome to ACCU. My name is Bryce Adelstein Lelbach. I am a principal architect at NVIDIA, where I lead programming language design and evolution and some of our compiler efforts. So my job is to make every major language a GPU language, from Fortran to C++ to Rust to JavaScript, et cetera, et cetera, et cetera. So I'm involved in the leadership of many different programming languages. I chaired the Standard C++ Library Evolution Group and the American Programming Language Standards Committee. My girlfriend took these pictures of animals in the Galapagos. These were blue-footed boobies, and these are Galapagos penguins. No relevance to the talk whatsoever. So today, I want to teach you about the C++ execution model. And this model is what makes the C++ language portable. It defines a standard for multi-threaded execution that is broad enough that any platform can implement it, from the smallest DSPs to server CPUs and GPUs. And to do that, we are going to actually read through part of the C++ standard itself slowly. We'll discover the core concepts and the rules of the execution model and see how it works in the real world. So at the heart of the C++ execution model is the C++ abstract machine. The C++ abstract machine is a portable abstraction of your operating system, kernel, and hardware. The abstract machine is the intermediary between your C++ program and the system that it is run on. Now, the abstract machine isn't a piece of software. C++ doesn't have a virtual machine like languages such as Java or C#. The abstract machine, it's just an idea. It's a concept. It's a notion. It's not like a real concrete thing. It's just words in a very long standards document. The idea is that you write portable code in standard C++, and then you want to deploy it on a diverse range of concrete systems. And your code gets mapped onto the abstract machine, and then many different platforms implement that abstract machine. And then that gives you portability. So C++ programs describe operations that are performed on the abstract machine. And C++ implementations define the characteristics of the abstract machine and translate operations on the abstract machine into operations on the system. So implementations only have to behave as if they implement the abstract machine. So an implementation is free to disregard any requirements as long as the result is as if the requirement had been obeyed, as far as can be determined from the observable behavior of the program. So for example, an implementation doesn't actually need to evaluate an expression or store an object if it can deduce that its value is not used and has no observable side effect. So this is known as the as-if rule in C++. You'll hear compiler people talk about this a lot. So the abstract machine's model is very, very simple. It is a collection of threads that execute operations on objects that reside in flat global storage. And so there's two key components here: threads and storage. So storage is flat. It has no notion of hierarchy, no notion of caches, etc., as far as the abstract machine is concerned. And objects reside in storage at a single memory location. Every byte has a unique address, and no two bytes will have the same address. So some objects may not have a unique memory location. For example, eligible empty base classes and objects that are marked with no unique address. An implementation is allowed to store two objects at the same machine address or to not store an object at all. For example, let's say that you have an int and you never take the address of it, you never modify it, and its value is a literal. Then the implementation doesn't need to store it because you cannot observe that it is not stored. So an object cannot have more than one memory location. If an object could have two addresses, we would no longer be able to compare object addresses to check for equality. So consider the self-assignment check in this assignment operator. Now, this is just one particular example. There are many far-reaching consequences of the object model. Compilers can even optimize based upon guarantees like this, so we can't easily break them. So every thread in a program can potentially access every object and function in a program. So now let's look at some example memory systems and evaluate whether they can follow this particular rule and implement the C++ abstract machine. So how about this system here? It's very straightforward. We've got a single processor, single set of memory for that processor, a single virtual address space. The answer here is yeah. This can implement the C++ abstract machine. Now, what if we've got two processes, separate processes running on this CPU, and they've both got their own private memory, and they've also got some shared memory? Does this work? Well, no, because this cannot, each of these processes individually is an implementation of the abstract machine, but the entire thing cannot be thought of as an implementation of the abstract machine because you've got threads in process 0 that can't access objects in process 1. So this means that things like shared memory, IPC, RDMA, distributed programming via things like MPI, those are all outside of the standard C++ model today. Even something like mmap. People always ask, why don't we have a stood mmap? The reason is because we'd have to redesign the C++ abstract machine a little bit to make that work. So what if we have a system with two types of processors, each with its own distinct memory that is inaccessible to the other? So this still violates the C++ storage model. I suspect that is coming from the other room. So this still violates the C++ storage model. We can't have objects that are not globally accessible. So this means that a heterogeneous system with both a CPU and a GPU needs to have some form of unified memory to support standard C++. Okay, so now let's move on to the key component, the primary agent of action in C++, which is threads of execution. So what is a thread of execution? It is a single flow of control in a program that evaluates a function call. And threads may run concurrently. And that's really when all of the trouble began, when we allowed the threads to run concurrently. So there's the main thread of execution in a program, which evaluates the main function. So you've always got at least one thread. Stood thread and stood J thread also create a thread of execution, which evaluates the invocable object that is passed to them. So let's talk about how initialization interacts with threads. So variables with static storage duration are initialized as a consequence of program initiation. So static objects will be constructed before main and then destroyed after main. And variables with thread storage duration are initialized as a consequence of thread execution. So threads essentially evaluate a function call, and that's how we should think about them. But what exactly does it mean to evaluate a function call? To understand what evaluating a function call means, we first have to understand what evaluation means. And to understand evaluation, we first have to understand expressions, because that is what evaluation operates on. So an expression is a sequence of operators and operands that specifies a computation. Sub-expressions are part of a larger expression. So for example, here we have a statement that declares and initializes a variable of type t. So it contains a number of subexpressions, a call to the constructor of t, an indirect function call, a dereference designating the function being called, and the expressions producing the arguments to the function call. So full expressions are top-level expressions. They're defined as any expression that is not a sub-expression. Full expressions may include sub-expressions that are not lexically part of the expression, such as the end of a scope, which we'll call destructors, or a function call which may have default parameters that get evaluated. So such implicit calls are considered expressions for the purposes of the execution model. So evaluation of an expression includes value computations and the initiation of side effects. Side effects change the environment. They can be reading a volatile object or modifying any object, calling a library I/O function, or calling a function that does any of the above. So let's take a look at an example here. So what the side effects of A equals A plus B, we're modifying an object. What about the cout here? Well, we're calling an I/O function. That's what cout is. And what about foo? Well, we don't know because we don't have a definition of foo, but whatever side effects foo would have, this expression would have those side effects. Value computations are pure and have no observable effect. The completion of the execution of an evaluation does not imply completion of its side effects. Stuff may happen asynchronously. So when we complete evaluating this expression here, it doesn't necessarily mean that the I/O has happened. Now we've reached one of the three key relationships that define ordering and thus concurrency in C++. And that relationship is sequenced before. So given any two evaluations, A and B, within the same thread of execution, if A is sequenced before B, then the execution of A shall precede the execution of B. So the sequence before relationship is asymmetric. So if A is sequenced before B, that means that B is not sequenced before A. And it is transitive. If A is sequenced before B and B is sequenced before C, then A is sequenced before C. So each full expression is sequenced before the next full expression in program order, in the order that you've written the code. So here, A is sequenced before B. If A and B are indeterminately sequenced, then either A is sequenced before B or B is sequenced before A, but it is unspecified which. So this means that A and B are not interleaved. That's the only guarantee that you get. If A and B are unsequenced, then A is not sequenced before B, and B is not sequenced before A, which means that they may be interleaved. It'll make a little bit more sense when we look at an example. So if A is sequenced before B, then A executes before B. So this is serial execution, which is what we typically think of. If A and B are indeterminately sequenced, then one of them executes before the other, but we don't know which. So this is thread parallel execution. And if A and B are unsequenced, then their execution may potentially overlap. So this is vector parallel execution or thread parallel execution that went really wrong. So let's look at an example using C++ 17's execution policies. So here we use the stood execution seek policy, which guarantees that each iteration is sequenced before the next iteration within the same thread. If we instead use the par execution policy, the iterations may be executed in parallel by multiple threads, but they can't be interleaved. If we use the stood execution on seek policy instead, then the iterations of the loop may be interleaved within one thread. And this interleaving is useful because it enables vectorization. It allows us to coalesce operations into these batched vector instructions. So what about statements? Insofar as the execution model is concerned, it's best to think of statements as just being compositions of expressions. So here, statement 0 is sequenced before statement 1. The condition of an if statement is sequenced before the body. And the condition of a while loop is sequenced before each evaluation of the body. So next, let's look at how operators are evaluated. So the value computations, but not the side effects, of an operator are sequenced before the value computations, but not the side effects of its operands. So the operand expressions to the following operators are sequenced left to right. And then for assignment, they are sequenced right to left, which makes sense. You want to figure out what you're assigning before you figure out what you're assigning it to. All right, so now we finally reached function evaluation. Remember, the whole reason we took this journey was we wanted to understand what threads do, and what threads do is evaluate a function. That's all that they do. So now let's dive into function evaluation. So when calling a function, every evaluation within the function and every evaluation not within the function are indeterminately sequenced. The expression designating the function is sequenced before the argument expressions. This is logical. You need to know what you're calling before you figure out what parameters you're going to call it with. Each argument expression is indeterminately sequenced with all other argument expressions. And every expression in the body of a function is sequenced after the expression designating the function and every argument expression of the function. Again, this makes sense because you need to evaluate the arguments and the thing that you're going to call before you can evaluate any of the code inside of the thing that you're going to call. So let's look at an example. Here we've got a function b, which takes 2 parameters and has a body e. And we've got a call to another function g, which takes 3 parameters. The expression a, an expression containing an indirect call through a function pointer to b, and the expression f. So the call to b takes 2 parameters, the expressions c and d. So the expression designating the function being called, the dereference of b punter here, is sequenced before the argument expressions to that function call, which is c and d here. And again, this logically makes sense. You want to determine what you are going to be calling before you determine what you'll be calling it with. The arguments to a function call are sequenced before the body of the function. Again, this logically makes sense. We have to evaluate the arguments before we start evaluating the function. And then all of the arguments to a function are indeterminately sequenced. So C and D are indeterminately sequenced. We don't care in what order they are evaluated, or rather, the implementation makes no promises about that. You might care, the implementation doesn't. Now, every evaluation within a function, like E here, and every evaluation not within the function, like A and F here, are indeterminately sequenced. That is, we don't interleave observable stuff from outside of a function with stuff inside of the function, even when we do inlining. And likewise, A, F, and the rest of the B call are indeterminately sequenced. And then finally, A through F are all sequenced before the body of G. So together, these 4 rules describe the sequencing of our function calls, which ultimately describes the sequencing of our entire program, as we can really think of our program as just being a collection of function call evaluations. You can think of operators as just being fancy function calls that have some slightly different evaluation rules. So now that we understand the basics of sequencing, we need to introduce 2 more relations to understand how concurrency works in C++. Because remember, we said that sequence before was a relationship that is only between things that happen within the same thread. So we need 2 relationships to define ordering between things across threads. And the first of those is synchronizes with. So a library operation A may synchronizes with other library operations B performed by other threads. So synchronizes with is not a symmetric relationship. If A synchronizes with B, that doesn't mean that B synchronizes with A, although in some defined cases that may happen. There are many standard library operations that will achieve the synchronizes with relationship, such as atomic acquire and release, personally my favorite, mutex lock and unlock, thread create and join, and barrier arrive and wait, and parallel algorithm fork and join. So synchronizes with is a runtime relationship. You only have it if the operation sees it. So imagine that we have 2 threads communicating data with an atomic flag. The first thread stores to the data and then does an atomic store release to the flag. So if the load on the right sees a value of 1, then and only then do we have a synchronizes with relationship from the left to the right. If the second thread does a load acquire of the flag, and then it can load the data if the flag was set. So if and only if that flag was set, we have the synchronizes with relationship. Now, if the load doesn't see the store of true, then we don't have a synchronizes with relationship in either direction. You cannot synchronize from a load to a store. You can only synchronize from a store to a load. Another example, mutex unlock operations synchronize with all subsequent mutex lock operations. So next we have the most important ordering relationship, which is happens before. So given any 2 evaluations, x and y, if x happens before y, then x is sequenced before y, or x synchronizes with y, or for some evaluation z, x happens before z, and z happens before y. So the happens before ordering describes arbitrary concatenations of sequences before, which is the ordering within a thread, and synchronizes with, which is the ordering between threads. So all operations within a thread that are sequenced before a synchronizes with will be observable to the other threads that are participating in that synchronizes with. So let's revisit an example from earlier to understand this a little bit better. So here in this example, the left thread stores non-atomically to data and then does an atomic store release to the flag. The store to data is sequenced before the atomic store to the flag. So the data store happens before the flag store. And likewise, the atomic flag load on the right is sequenced before and thus happens before the non-atomic data load. Now, if the flag load on the right sees the flag store of true, then it synchronizes with that flag store, and thus the flag store happens before the flag load. And the data store happens before the flag store, and the flag store happens before the flag load, and the flag load happens before the data load. So therefore, transitively, the data store happens before the data load, even though the data store and the data load are not atomic. Now, happens before doesn't mean happened before. Now, if you were able to write a program that witnesses this, then your program has undefined behavior. But what I'm getting at here is that the happens before relationship does not tell you anything about the temporal order in which your processor did things. It just tells you about the observable order in which things happened, because processors are very, very asynchronous, which we might talk about if we get to that bonus talk. For example, consider the function foo here. So it sets x to y plus 1, and then sets y to 1. So the assignment to x is sequenced before the assignment to y. But if you look at the assembly for this code on some compilers, you'll see that the assignment to y may actually be interleaved with the assignment to x. So here, first we load y into a register, then we store 1 to y, and then we add 1 to the value in the register, and then finally we store that value to x. So things are happening asynchronously here, but it's fine because we can't observe it. So happens before doesn't mean happened before. A happens before relationship doesn't mean that x actually occurred in time before y. This is all about observable behavior, not actual behavior. Now, a well-defined program is guaranteed to observe things in the happens before ordering, even if that's not what actually happens under the hood. And likewise, happening before doesn't mean you have the happens before relationship. So just because x occurred in time before y does not imply that x happens before y. In one particular execution of your program, or even in most executions of your program, x may occur in time before y, but that is no guarantee. It may happen to work, but that doesn't mean that you have a happens before relationship. You only have that if you've followed the rules, used synchronization primitives, and established such a relationship. So if you rely on ordering that is not guaranteed by happens before, then you have a data race. And a data race starts with conflicting operations. So two expression evaluations conflict if one of them modifies a memory location and the other one reads or modifies the same memory location. So a data race occurs when you have two conflicting operations performed by different threads, at least one of which is not atomic, and neither happens before the other. So any such data race results in undefined behavior. So consider this program here. We're communicating an int between two threads, and this int is initialized to 0 before we create the threads. The producer thread writes 42 to data. And then the consumer thread reads from data and prints it out. So we have two threads performing conflicting operations, at least one of which is non-atomic, and there's no happens before relationship. And so we have a data race and thus undefined behavior. And so this program could print 0, it could print 42, or any random integer value. It could also print nothing at all. It could crash, it could do whatever. Now, if we introduce a synchronization primitive, such as a semaphore, we can get a happens before relationship. So the release in producer synchronizes with, and thus happens before, the acquire in consumer. The stored to data happens before the release, and the acquire happens before the load, so therefore the stored to data happens before the load of the data. And so this program will print 42 as we intended. We could also use an atomic flag and acquire release semantics to get the same happens before relationship. So here we're using atomic's wait interface to block until we observe the producer's store. But if we use relaxed loads and stores for the flag, we won't get a happens before relationship between the store and load. Relaxed loads and stores are not synchronization operations, so we'll be back to undefined behavior. Now, if we instead make the data itself atomic and do a relaxed store and a relaxed load, we'll have a well-defined program. We don't have any happens before relationship here between the threads, but all of the conflicting operations are atomic. So we do not have a data race. What's interesting about this program is that what it will print is indeterminate. It's going to either print 0 or 42. It will never print anything else. It will print one of those two things, but you don't know which of those two things it will print. So this is still, perhaps not the best way to write code, but there are some circumstances in which this is perfectly fine. But there's a big difference between this code here, where it's going to be one of these two outcomes, and the undefined behavior that we saw a few slides ago, where it could print 0, 42, it could print a partial value, it could crash, it could do any number of things. So we now understand threads, how they evaluate expressions, how those evaluations are ordered, and what data races are. And the final thing that we must learn is what guarantees we get when threads block or wait on something. So an execution step is the termination of the thread, an access of a volatile object, or the completion of a library I/O function. And I think what I forgot to say was that the evaluations executed by threads are delineated by execution steps. Also, or an atomic operation. So blocking is waiting for a condition to be satisfied before continuing execution. So blocking library functions are considered to continuously execute execution steps while waiting for their condition to be satisfied. A thread of execution makes progress when it performs an execution step or a lock-free execution that does not complete because other threads are making progress. So some atomic operations may fail spuriously due to interference from other threads, and implementations are encouraged but not required to prevent spurious failures from indefinitely delaying progress. So for example, on load-locked store conditional architectures such as ARM, another thread may repeatedly steal the desired cache line for unrelated purposes in between the load-locked and store conditional instruction, which is how you'd implement atomic loads in stores. And so on those architectures, weak compare and exchange operations may fail spuriously. Even when the atomic's object's value is equal to the expected value, it may fail to complete successfully. And what the standard is saying is that it encourages implementations to not make that a pathological thing that happens forever. So forward progress guarantees that something observable should eventually happen. Implementations may assume that all threads will eventually perform an execution step, aka infinite loops have no observable effects, are undefined behavior, and the compiler can just delete them. Now finally, we can talk about forward progress guarantees, which is the last piece of our talk. And there are three: concurrent forward progress, parallel forward progress, and weakly parallel forward progress. So concurrent forward progress gives you the guarantee that the thread will make progress regardless of whether other threads are making progress. So examples of concurrent forward progress include preemptive OS scheduling algorithms such as fair share and round robin, an unbounded thread pool that will add new OS threads to the pool as needed to make progress. Parallel forward progress gives you the guarantee that once the thread has executed its first execution step, the thread will make progress. So once it is started, it will run to completion. So examples of parallel forward progress include tasking frameworks where tasks cannot be interrupted, such as a bounded thread pool or threads on NVIDIA GPUs. And then finally, we have weakly parallel forward progress, where the thread is not guaranteed to make progress at all. It's basically no forward progress guarantee. We just gave it a nice name. So examples of weakly parallel forward progress include non-preemptive OS thread scheduling, tasking frameworks that support task suspension, such as fibers, And then threads on old, very, very old, no longer supported NVIDIA GPUs and GPUs made by other companies that aren't as cool as us. So what guarantees do we get from the main thread? Well, it's actually just implementation defined, but the standard says implementations should provide concurrent forward progress for main. The reason that it's implementation defined is because on a lot of platforms, technically speaking, even the fair OS scheduling algorithms can't really make a guarantee that you get concurrent forward progress, because there's some types of interrupts and scheduling that for OS level stuff that could always, take precedent over whatever you're doing. And then what about stood threads? Again, it's implementation defined. So on most popular platforms with an OS, stood thread will give you concurrent forward progress. And on embedded platforms and platforms that have no threads, it may be weaker. And again, the standard says that implementations should provide concurrent forward progress for stood thread and stood JThread. So when library functions block, they need to ensure that progress is being made. And to do that, they must boost block. And in your code, you also need to do this to ensure that you don't impede forward progress. So boost blocking is when you block on the thread with weaker forward progress than yours, while preserving your thread's forward progress. So more specifically, when a thread P boost blocks on a set S of other threads, the forward progress guarantees of at least one of the threads in S is temporarily upgraded to P's forward progress. And this is repeated until the blocking condition is satisfied. So it's unspecified which thread or threads in that of execution in S are chosen and for which number of execution steps. So boost blocking ensures that your children threads make progress, not your siblings. So boost blocking does not prevent you from inhibiting the forward progress of weaker threads when using synchronization primitives. So let's work through an example. So here's a simple implementation of a thread pool with a fixed number of workers. So we have a queue of callables and a mutex. And execute async enqueues a callable and returns a shared putter to an atomic bool that will be set to true once the work item has been executed. This is a poor man's future or sender. It's fine. Then we have a wait function that takes one of the tokens returned by execute async and waits for it to be ready. So each worker thread in the thread pool executes process items, which contains this loop here. And the loop calls try-pop, which locks the mutex, and then checks whether there is work in the queue, and if so, it pops a task from the queue, and it executes it. The tasks in the queue can be thought of as threads of execution with parallel forward progress. We call these execution agents. So once they start executing, they will run to completion on the worker thread. Now, suppose one of the tasks enqueued in this thread pool wants to parallelize its work. So it spawns some children task to process part of the work in parallel. And then it performs part of the work itself. And then finally, it waits for the children to complete. But what happens if the thread pool has only one worker thread that's serving it? Then the worker will start executing this outer task, which enqueues the children and then blocks pending their completion. So the children will never complete because there's no other worker thread to execute them. It is necessary for our wait function to boost block, to pull tasks from the work queue and execute them until the blocking condition is satisfied. To fix this, we need to modify wait to boost block. Any thread that calls wait needs to ensure that the work it's waiting on will make forward progress. And to do that, they have to make sure the entire queue makes forward progress. To do that, instead of unconditionally waiting on the token for our task, we can check the token in a loop while also processing work items ourselves. So this donates the calling thread's progress to the work that it is blocking on. And so with this change, even if we have just one thread in the pool, this code will be fine. So when we hit the waits here, instead of blocking forever, we'll eventually execute the child task ourselves in the thread executing the parent task. So we've reached the end of our journey, for this talk at least. So to summarize, in the C++ execution model, threads evaluate expressions that access and modify flat storage. Evaluation within a thread is driven by the sequenced before relations, and interactions between threads is driven by synchronizes with relations. Happen before relations tie together sequenced before and synchronizes with relations. And forward progress promises eventual termination. So I've made a number of simplifications and ignored some corner cases like memory order consume, but we've deleted that, so I don't need to explain that anymore. Signal handlers messes with things too, but we can kind of ignore them for now. And if you want to learn more about parallel programming and algorithm design, my buddy Connor and I have a podcast, ADSP, Algorithms Plus Data Structures Equals Programs, available on all streaming platforms. You can go subscribe now. And additionally, if you want to learn more about GPU programming, we launched a whole track of CUDA developer content at GTC this year, which is NVIDIA's developer conference. We've also released a whole new CUDA curriculum focused around modern C++ with tutorial, and also Python, with tutorials, notebooks, and other learning materials, which you can find on our Accelerated Computing Hub on GitHub.